Hello, this is the presentation from EGCMS, and today we are talking about the data processing after microphone free field sensitivity calibration. And firstly, we're introducing the requirement of measurement of inaudible sound. And here is the list about the ultrasound application. As you can see, the lower bound are average located around the 20 kHz. Here, the upper bound of industrial exposure measurement will be 40 kHz. And the ultrasound application, such as treatment for drug addiction or therapy, will be up to megahertz scale. The calibration and measurement capacity, as known as CNC in each CMS, is from 20 Hz to 20 kHz, which cannot fulfill the requirement of application mentioned here. For instance, this figure shows the sound intensity at 40 kHz around the working machine. As you can see, the color bar shows that the value which is larger than 100 dB accumulate most of the portion in the figure. And here we are not discussing about the unproven effect of high-frequency sound to our health. But this fact makes us just exposed to this invisible sound, for there's no sound meter are calibrated for ultrasound frequency range. Therefore, the measurement standard to this high-frequency voice will be necessary. This research is mainly confirming the free field calibration of microphone sensitivity in 20 kHz to 40 kHz in order to expand the CNC. Currently, each CMC only provides a microphone calibration in pressure sensitivity, and there's no free field sensitivity calibration service for the free field type microphone. And therefore, we are paying effort to synchronize the technique with the international NNL by the expansion of frequency range of sensitivity calibration in free field microphone system, and also by the comparison calibration method. The free field sensitivity of laboratory standard microphones can be transferred to the working standard microphones. The microphone in practical application, as the previous page mentioned, can therefore be traceback in the free field sensitivity. And here, the sensitivity is defined as the ratio of pressure and voltage, which the unit will be the millivolt of Pascal. In the free field calibration, the reciprocity quality of microphone will be applied, where a microphone will transfer electric signal to some and act as a transmitter. The other one will act reversely as a receiver. During the calibration, the ideal situation is only the direct wave being recorded, but in reality, the reflection and standing wave between shells of microphones will also be recorded. So this redundant data will show ripple on the curve, and we are taking them out. By applying inverse Fourier transform, we can see the interval the first wave act. By affiliating the window, we can obtain the clean time signal, where the length of the window can be determined by the distance between microphones divided by the sound speed at the calibration condition. Here, we preset the middle of the window to be at the maximum value at the first wave, and it can be adjusted manually if the result deviates obviously from the original signal. After the clean data is scanned, and by doing Fourier transform again, the smooth curve with only direct wave can be obtained. Here, one thing is to mention, the extra wave generated from frequency above the natural frequency of microphone will be concluded in the direct wave, and this cannot be removed by this method. The voltage ratio is put in the model equation defined by the third part of IEC 61094, and the sensitivity of microphone can be determined as a function of frequency. And there's a 0.22 decibel difference by comparing the result from filtered and unfiltered signal. Also, we take the commercial light system into consideration, and the result shows a confirmable match for the variation is below 0.08 decibel in the calibration frequency range. The uncertainty during the calibration is defined as the square product of sensitivity factor and variation. The sensitivity factor will be the gradient of the parameter, which consists not only of the frequency but also other parameters like temperature, pressure, or humidity, voltage, etc. Therefore, under different calibration conditions, the sensitivity factor will also be different. By studying the model provided in third part of IEC 61094, the uncertainty can thus be precisely calculated by establishing measurement equations. And so, after the uncertainty is calculated, we can get the contribution varies in magnitude. For instance, the acoustic center and capacitance are in the scale of 10 to the power of -3, where they offer over 80% of the uncertainty contribution in the system. This breaks the rumor that the pressure varies a lot during calibration, and it will cause much uncertainty in the experiment. And in fact, it only possesses a portion below 1 per thousand, for it's at 6 decimal places. Through the calibration frequencies, the variation of uncertainty doesn't vary a lot. So here the pie chart shows the average contribution from 1200 Hz to 40 kHz. In time domain, we can choose the direct wave part without the reflection and standing wave by putting the window in the right position, and the clean data can be obtained. The sensitivity factor can be determined by the differential of the function given in third part of IEC 61094 as shown here. And therefore, we can have more realization of uncertainty sources. By above two results, the expansion of primary calibration frequency range to high frequency would be possible and confirmable. Thank you for paying attention.